by quantitative, but assigning a dummy variable or a dummy number to a certain data and qualitative data that's not converted to numeric. So let's keep that in mind. And so these are just a few statistical tests that can be done. So it means that in most hypothesis testing, we mostly want to test whether there's significant difference in the means. But to do that, you have to look at the structure of the data. There are instances where the data you are trying to compare whether there's significant difference between, let's say, two numeric data. But one data was collected at a certain time point, and the same data was collected at a different time point. And you want to compare whether there's significant difference in that particular variable across, let's say, two groups. In that case, a pair t-test is used for that. An independent t-test is when you are comparing between two independent groups. And then when we are comparing the means between more than two independent groups, then we use ANOVA. And then for ANOVA, you can also do a pairwise comparison test. We have Bonferroni, we have Shafi, we have Tukey, and so on and so forth. And there are instances where you have you want to do ANOVA, meaning that you want to compare a set numeric data across 3 or more groups, but that numeric data was collected at more than one time point. So in that case, you do something called repeated measures ANOVA. And then if we are now talking about, let's say, a particular numeric variable, you wanted to explore whether there's significant difference in the means between 3 or more groups, I said you would have gone for an ANOVA. But what if you have more than one numeric variable and you want to explore or investigate their respective mean differences between 3 or more groups? Then you do something called multivariate ANOVA. So that's what we call MANOVA. And there are also instances where I brought Esther here, but there are instances where you have, let's say, a certain variable, let's say you collected a certain data at some baseline time point, and then you've collected the same information at a different time point. And at the end of the day, you want to predict for the final time point. You want to see how some predictors or some specific variables could predict that data at a different time point. But you want to adjust for the initial the data at the baseline. So in that case, we go for something called ANCOVA. So with ANCOVA, it's just like the same regression models that we've been doing, but the only difference between ANCOVA and then ANOVA is that with ANOVA, you have a data that was collected at just a single time point, and you want to see whether there's a significant difference in the means of that particular data or variable between 3 or more groups. But situations where the same variable, you collected it as, let's say, time 0, and then you've also collected the same information at time, let's say, 24, or let's say time 12, meaning 12 months. And then the goal is that you wanted to predict for what are significant factors that influence, let's say, the scores at time 20, time 12, or the final time point. However, you believe that the data clearly, you can clearly see that the data, there was this repeated measures there, meaning that is the data obtained at, let's say, the initial time point, probably over time is either it increase or it decrease. So meaning that there's some association between the data at the previous time point and the data at the current time point. So if you want to predict for the current time point, some studies would also want to adjust for the data at the first time point or the initial time point. And the moment you add such a covariant data or a covariant variable in the data, we call it, in that case, we say you are trying to do an ANCOVA, analysis of covariance instead of analysis of variance. And most of the times in ANCOVA, we are also interested in exploring interaction effect as well. So so keep in mind, I didn't mention, bring it here, but it's also another class of model out there. And then if the normality assumption, meaning that if the data is not normally distributed, then in that case, it means instead of doing the means, you go for the medians. So it means I've actually specified in such a way that for the pair t-test, its non-parametric version is called the Wilcoxon sign test. And for the independent t-test, its non-parametric version is called the Mann-Whitney test. ANOVA, its non-parametric test is called Kruskal-Wallis, and so on. This is to say, if you want to do any statistical analysis, you really have to understand these things before you start thinking about programming, thinking about trying to explore much about your data and so on and so forth. Now, when you talk about the Friedman test is the non-parametric version of repeated ANOVA. So these are things. So there are so many tests out there. So depending on your need, your objectives, you then identify which test is appropriate. And always don't forget to test if for parametric assumptions, especially if your data is normally distributed or not. And if it is not normally distributed, then you go for the non-parametric version. Now, this is, I think, the last bit before we start the proper programming. So the last bit is about regression analysis. So most regression is one of the most popular statistical methods out there, because almost every field, most of the times we are more interested in investigating some predictors or determinant of a certain variable. Now, one thing you have to notice that the nature of the dependent variable. So when you say the dependent variable is what you aim to predict, or what you want to explore some factors, how some factors affect it. And then, so if it means that if I'm interested in investigating maybe significant factors affecting, let's say, performance of students, then it means performance of students, in this case, is my independent variable. Maybe I would want to quantify that based on maybe GPA or something. So that is what we mean by dependent variable. Now, independent variables are those variables that you are not interested in them, but you want your focus is that you want to see how they affect or predict the dependent variable. So keep in mind that the dependent variable could be categorical. And when it's categorical, it could have either 2 levels or more than 2 levels. And there are instances the dependent variable would be a discrete variable. Discrete in this case is that it takes it's a count data. So it means it cannot take fractional values, something like number of road accidents. So it means, let's say, if I'm interested in looking at factors, or let me say I'm interested in determinants or factors affecting the number of road accidents in a certain country. And then also I'm interested in factors affecting the proportion of road accidents in a certain country. The models I will use will be different, just because one is looking at the number of road accidents, the other is looking at the proportion of road accidents. And the reason is that the number of road accidents is discrete. So it means it can't take a fractional value. It can't take, the number of road accidents cannot be 2.5. That's what I mean by it can't take a fractional value. But when you explore the proportions of road accident, then in that case, you would have proportions, like something that could be 0 point something and so on and so forth. Fine. Now, one thing you have to notice that in order to do regression analysis, the nature of the dependent variable and the structure of the data are 2 most important things that determines the choice of regression analysis you can perform. So let's say you want to perform a regression, you want to do regression, and the dependent variable is continuous. When it is continuous, of course, I said you would explore some parametric assumptions and so on. But for now, I'm just going to focus on how do you decide which regression model is imperative for a particular data, depending on the data structure and also depend on the nature of the dependent variable. So in regression, there are 2 key things. The 2 key points are that the nature of the dependent variable, whether continuous, discrete, or categorical, will determine the type of regression model you want to consider. And if the data also is collected at a single time point or more than 1 time point, then that will also inform another class of regression models you can use. So now we are going to talk about fixed effect regression models. So when you say fixed effect regression models, they are models that are strictly used for cross-sectional data. So what do I mean by cross-sectional data? I will show, I was supposed to add some visuals to explain what cross-sectional data, but that's fine. But I've touched these on, so on the YouTube channel, there's a video on the most important things you need to know in statistics. I've really covered all these things in detail. So when you say cross-sectional data, we are talking about a data that was collected at a single time point, but you collected several variables. So let's say you are doing a study, and for the study, it means that for cross-sectional data, each row corresponds to a single individual. So it means a single individual cannot have more than 1 row. So that is what we mean by a cross-sectional data. And when you talk about a longitudinal data, so longitudinal data is a data, it's when you collect cross-sectional data at multiple time points, then we have a longitudinal data. But there are instances where a data is cross-sectional, but there's repetition for some few participants, or there's repetition for some few individuals. In that case, we call that data a pooled cross-sectional data. But a pooled cross-sectional data somehow, one could say is a longitudinal data. But for longitudinal, we expect each of the individual to have at least more than one time point of data. And then all longitudinal data are also known as panel data. So anytime you hear panel data, it shouldn't be any big thing for you. Panel data is simply a longitudinal data. So, and then for a longitudinal data or panel data, it's a cross-sectional data that has been collected more than one time point. And when we say cross-sectional data, what we are saying is that, let's say you are doing a study, you collect information on height, weight, gender, other variables. You've collected multiple variables at a particular time point for each individual. And that is what we mean by a cross-sectional data. So it means for a data to be cross-sectional, there should be more than one variable collected at that particular time point. And each individual is information about each individual is collected once. So it means each row corresponds to a particular individual. So that's just a quick overview of cross-sectional data, longitudinal data, and keep in mind longitudinal data are also known as panel data. So it means if you want to do a regression and the data is cross-sectional, the class of regression models you are going to use is completely different from if you want to do a regression for the same problem, but in this case, you collected the data at more than one time point. Then it means you have to choose some other class of regression models to deal with that. So basically, all the models I'm going to talk about here for the case of the cross-sectional, all those models also applies to the longitudinal case. Nonetheless, the only difference is that for the cross-sectional, the model are called fixed effect models. And then when the data is longitudinal, you're going to use something you call mixed effect models. And then so it means that for the instance where the data is cross-sectional and then the dependent variable is continuous, you are going to use OLS regression. OLS regression has some specific parametric assumption. It expects the dependent variable to be normally distributed, and it expects also some homoscedastic assumption concerning the variance to be constant. But one thing you have to, that is in terms of the dependent variable. But one thing you have to notice that some of these assumptions will be violated depending on the data you're working with. So it means there are other versions when the data is continuous. Example is one could consider weighted least squares, one could consider generalized least square regression. All those methods are used when there are violations in the parametric assumptions. Fine. And then situations where the dependent variable, maybe you want to predict the prevalence of your focus, you want to identify determinant or factors affecting maybe the prevalence of HIV. So it means your data is your data, the dependent variable is whether you have HIV or not. So in that case, it means your dependent variable is categorical. So if your dependent variable is categorical, then you use a class of regression models called logistic regression. Okay, and then if the categories are just two, then it means you're going to use a binomial logistic regression. But if, let's say, you are predicting the grace of, let's say, an infection, and that's the dependent variable, and the grace, we have, let's say, 3 or more grace. So it means they are not just two. So it means you cannot use a binomial logistic regression. So in that case, you use some class of regression model called multinomial logistic regression. If the dependent variable is count, meaning discrete, that is, let's say you are predicting the number of, let's say, road accident. So in that case, you use something called Poisson regression. Now, Poisson regression expects the mean and the variance of the dependent variable to be equal or significantly or insignificantly different. But when that assumption is violated, then we use other class of Poisson regression, one called quasi-Poisson or negative binomial regression. Now, in the case of when the dependent variable is count, if the mean and the variance are not equal, then we say there's dispersion in the data. And so the dispersion could be an over dispersion or under dispersion, whether the variance is less than the mean or the mean is greater than, or the variance is less than or greater than the mean. So that will determine whether there's over dispersion or under dispersion. So the negative binomial regression and the quasi-Poisson regression, they are more robust to the violations from that assumption. All right, so situations where now for the same class of model you wanted to consider, the data was cross-sectional, then it means we are going to use fixed effect. So all these models I've mentioned are fixed effect regression. So fixed effect regression is basically fitting in a regression model to a cross-sectional data. Now, the moment the data was collected at multiple time points, what it means is that you have to account or tell the software or whichever statistical software you're using that there's pseudo replication in the data, or the data was collected at more than one time point. And when that situation happens, what that means is that you have to you have to account for the temporal replication in the data. So in order to do that, we have something called random effect, and we have fixed effect. So the fixed effect in the case of longitudinal data, they are the predictors of interest. So let's say you have some specific independent variables that you want to check how they affect a certain predictor. So, and then those, how do you call it? Those independent variables of interest, they are what we call the fixed effect variables. But the random effect variables are those variables that are not of interest to the researcher. Nonetheless, it captures the structure of the data. So a situation may be where they collected data over time and also collected data at specific, let's say, countries or specific sites over time. Those in agriculture and those in, let's say, into biology, most of the times you realize that they mostly do experiment at more than one time point, and sometimes they would have different sites or location and will collect data at multiple times also at those locations. So it means there's something you call replication due to space. So that is, to make it a little bit technical, we call it spatial pseudo replication. And then when you hear temporal pseudo replication, it's just when there's repetition in time. So basically what we are saying is that if the data is longitudinal, let's say there's repetition in time, it means you have to indicate the time variable as a random effect in the model. Though you are not interested in predicting time, but you have to indicate that in the model to tell the software or to indicate that there's temporal replication or there's repetition in time. If you don't do that and you fit a fixed effect model to a longitudinal data, it means all the regression output, everything is wrong. And the funny thing is that any wrong thing you do, you get an output. So getting an output, it does not imply it is correct. So that is why you have to really understand these things. So that is introduction to generalized linear mixed model. So it means generalized linear mixed model is just the fixed effect model that we have already mentioned for the cross-sectional case, but just at this time around, since there is repetition in either time or space, you need to include those variable as random effect in the model to account for that. And that is what brings about generalized linear mixed model. So it means we could have a generalized linear mixed model in the case of OLS regression, in the case of a logistic regression, in the case of Poisson regression, and so on and so forth. And there are softwares and R packages to help you do this easily in R or any other statistical software. Now, this class of model is called generalized additive models. Now, these additive models is something that just a few people uses it, and just a few people are aware of that. So when you talk about the additive model, so you realize that there are instances where you have a continuous dependent variable and you have some continuous independent variable. But you see, we are saying that you are fitting a linear regression model. So linear regression model in this case implies that the covariate or the predictor should be linearly related with the dependent variable. Okay, it means it should be linearly related with the dependent variable. But what if this linearity assumption is violated? What if there are instances where there's a certain continuous variable that is non-linearly related with the dependent variable? Does it mean that you will still want to fit a linear model? It means that in that case, if you fit a linear model where some of the predictors, not all necessarily, but some of the predictors are non-linearly related with the dependent variable, it means you are doing something wrong. So it means that's why to do any regression, you have to do some explorations first, just to be sure that the parametric assumptions are met. If they are not met, it doesn't mean you cannot still test your hypothesis. It only tells that you should choose a correct model for that. So the additive models are used in situations where for a particular continuous predictor, there's nonlinear relationship with, let's say, with the dependent with the outcome variable or the dependent variable. So what we do is that we fit something called splines to those variables that have nonlinear relationship with the predictor variable. And by fitting splines, we are trying to smoothing out that nonlinearity to make them fairly linear before you now do your regression. So it means that the additive models I mentioned is just the first two class of models, just that this time around, those predictors that are having nonlinear relationship with a dependent variable, you fit splines to those variables. By fitting splines is just a simple addition to the code. So it's nothing, it's not a big deal. And with that, it will now smoothen out the nonlinearity so that you can now impose or use a linear model for that. Now we have class of model called machine learning or deep learning techniques. And these models are really, really useful For these models, we don't really care about parametric assumptions. We really don't even want to care about the structure of the data and so on and so forth. So for machine learning, one thing you have to notice is that we have different areas of application. So it means someone would be using machine learning in the context of regression. So it means we have regression-based machine learning models. We have, let's say, time series-based machine learning models. Someone could be doing image processing. So it means we have machine learning for image processing and so on and so forth. And all these machine learning techniques, we could also apply to both cross-sectional and longitudinal data as well. And in order to fit a regression model, there are instances where we have so many variables and we don't know which one to use. In clinical trials, most of the times the research team or the clinicians have specific variables they are interested in. So with that, we don't care, we don't want to do something we call variable selection. So it means for clinical trials, no one uses variable selection in those cases because they know exactly what they want to investigate. But in situations where you are working with, let's say, an observational study, or you collected a certain data from a secondary source, and then you want to, but there's a particular predictor variable, but there are so many independent variables and you're not too sure which one you should use. So there are class of models or class of variable selection techniques out there that will help select the predictors that we believe that would have or would achieve the highest predictive power when you fit the model. So we have stepwise regression. So it means for stepwise regression, what you do is that you fit your standard regression model. The moment you now apply the stepwise regression to the output of the model, what it does is that it determines the subset of the model or which subset of variable would have the best model fit. So that is what we mean by stepwise regression. And for the penalized regression methods, such as ridge regression, lasso, elastic net, what they do is that, keep in mind, ridge regression is, so the lasso and the elastic net, apart from the fact that they are used for variable selection, they can also be used for data reduction. Ridge does not do data reduction or reduction of variables, but it's not something I want to cover in this lesson. But these penalized regression are instances where if you want to fit a regression model, we expect that your predictors should be able to predict or relate with a dependent variable. However, we don't want the independent variables or the predictors to have any high correlation between themselves. Situations where that happens, we say multicollinearity has occurred. So multicollinearity are situations where some predictors or some independent variables have high correlation between them. And when that happens, there are three serious issues that can pop up. Either if your overall model is significant, it means naturally, if your overall model is significant, what that implies is that at least one of your predictors or one of your independent variables was significant. If all your independent variables are insignificant, statistically, we expect the overall model not to be significant. But when there's multicollinearity, what happens is that your overall model can be significant, but none of the predictors is significant, or at least one of your predictors is significant, but the overall model was not significant. This is to say that when multicollinearity is present, you are virtually going to end up having wrong results. And there are ways of testing for multicollinearity using some quantities, for instance, variance inflation factor, tolerance, and so on and so forth. So this is just, and so beware of multicollinearity and its effect anytime you want to do any form of regression model. So to wrap up on that, what I'm saying is that in order to do a regression, always keep in mind that the nature of the dependent variable and then the structure of the data. So when I say the nature, it means whether it's continuous, numerical, categorical. And what I mean by the structure is that whether the data was collected at a single time point, which is cross-sectional, or the data was collected at multiple time points, which is longitudinal or panel. Okay, if the data is longitudinal, apart from generalized linear maze models, one could also consider another class of regression model called panel regression. And keep in mind that all these, the generalized linear maze model, the generalized linear model, that is the fixed effect model, and the additive model, these are all predicting means. But there are instances where the parametric assumptions we expect the dependent variable to be normally distributed, and we expect the error distribution to also be normally distributed, meaning that the residuals to be normally distributed. These are specific parametric assumptions. You don't need to understand all these things. I just want you to have a fair idea. But when these assumptions are violated, if I was doing a statistical test and then I wanted to use a t-test and the data was not normally distributed, you remember we'd have done a median test using a non-parametric test. What if you are trying to fit a regression model and then there's the normality assumption specifically for the dependent variable was not met or was violated? It means instead of predicting the means, you should rather be predicting the medians. Keep in mind that almost every linear model are mostly predicting the means. Okay, they are predicting the conditional means. Fine. So in situations where the dependent variable is not normally distributed, maybe and then situations where maybe the parametric assumptions of the classical regression model were violated, then we now can predict the medians rather than the means. And that brings us to some class of regression model called quantile regression. These are kind of regression model that only a few people explore, but keep in mind that it's not always compulsory to predict the means. To be frank, if the data is normally distributed, predicting the means and the medians are the same. So it means that statistically, the median is more robust than the means. The reason being that if the data is normally distributed, there's no significant difference between the mean and the median. However, if it's not normally distributed due to, let's say, skewness or maybe due to outliers, then in that case, you would want to consider the quantile regression to rather predict medians. And apart from just predicting medians, you can also predict other quantiles of the data. It means you can predict maybe the first quartile or let's say the 25th percentile of the data and so on and so forth. And so these are something you should look into it. Fine. So I'm done with all those details, boring details. So I'm happy that you still stick with me. But these are very important in that it means that we just don't get a statistical software, start doing analysis. In the software, you would always get an output, but not every output is correct. So interpretability is very important. And this is why I thought it was imperative to touch on these things.